Alrighty, let's go ahead and jump into 7.3. 7.3 is going to be on proving triangles are similar. So once again, you guys probably remember that in chapter 4, we started out by talking about what congruent figures were. And then we talked about how to prove that figures were congruent, and we did it the long way. We went over and showed all sides were congruent to all corresponding sides, and then all angles were congruent to corresponding angles. And sometimes you would have to check all angles and all sides. For example, if the figure was not a triangle. But then, as we moved on to 4.2 and 4.3, we started looking at, is there an easier way to do this? The lazy and efficient part of us came in and we said, I really don't like checking 6 things if I was working with a triangle. Is there any way I could check only 3 of them? Maybe I just check the angles or just the sides? And we found out that there were shortcuts to proving that triangles were congruent. So it says a few chapters ago we studied congruent triangles, and at first we had to check all the angles for congruency and all the sides. Soon we learned that there were shortcuts that could be taken to determine if the triangles were congruent. What were those shortcuts? So you probably remember one of them was SSS. If all sides of one triangle are congruent to all sides of the other, the triangles are congruent. Then we looked at SAS, we looked at ASA, we looked at AAS, and we looked at HL. Those were all the ways that we could prove that 2 triangles were congruent, all right? And that was the lazy and efficient way of doing it so that we figured out the least number of things we had to check. And remember how we did that was we found out that, let's say we had a triangle that had side lengths of 3, 4, and 5. We learned there was only a single triangle that could be created with those sides, meaning knowing these sides kind of lock the angles in. So knowing that all sides of one triangle are congruent to all sides of the other was enough to prove that the whole triangle was going to be congruent to the other one. So now what we're doing is we're going to look at similarity, all right? We're not going to spend as much time as we did with congruency, but here, let's go ahead and jump straight into the different postulates, the different ways we can prove 2 different triangles are similar. One of the ones we looked at when we were trying to prove congruency was AAA. And we found out AAA was not a way that you could prove 2 triangles were congruent. For example, this little tiny triangle could be a 60, 60, 60, and then you could have had a bigger triangle that was also 60, 60, 60. So you had 2 different triangles that were not congruent, that had all of the angles being congruent to all the angles. That was not a way that we could do congruency proofs, but take a look at those. These 2 figures are the same exact shape, but just a different size. What do we call that when they're the same shape, but not necessarily the same exact size? Similar. Okay, so this is the one of the ways that we're going to prove that 2 triangles are similar. A shortcut way rather than having to check all angles and then check all the sides being proportional. And that is called AA. If 2 angles of one triangle are congruent to 2 triangles of another triangle, then the 2 triangles are going to be similar. All right. Now you might ask yourself, AA? I thought we had to do AAA, 3 A's. Well, this just proves how lazy and efficient mathematicians are. They know there's a thing called the third angles theorem, and they know if 2 angles are congruent to 2 angles, then the third angles are congruent. So that brings the lazy and efficiency level to a whole new level by saying, well, so I can just check 2 of the angles and that's enough? And the answer is yes, because the third angles theorem tells you that the third angles will also be congruent. So that's why we call it AA postulate. The next one is going to be Sas of Similarity. Now this one is kind of like SAS that we've used, except for one small tweak. And how it works is if an angle of one triangle is congruent to an angle of another triangle, and the sides of the that include the two angles are proportional. So the difference is normally the sides would have to be congruent for normal SAS. Now we're looking to see if they're proportional, and if they are, then the triangles are similar. So we have SAS of similarity, and you have to say of similarity because normal SAS is for congruence. And the last one is going to be SSS of similarity. If the corresponding sides of two triangles are proportional, then the two triangles are going to be similar. So it's kind of like normal SSS, except for instead of looking at the sides being congruent, we're looking to see if they are proportional. Those are going to be the three shortcuts we're going to use. So you might be sitting there going, but what about, isn't there like an ASA of similarity or an AAS of similarity? My answer to that is, look what is embedded inside of ASA. AA. If you can already finish a proof by AAA, then why would you keep going to look at the S part? I'm sure there is an ASA of similarity, but once again, the lazy and efficiency part of us goes, well, we already have the two angles, so we're good. We don't need to have a different way to prove they're similar that adds on an extra component that we don't need. Same deal here. We already have AA, so there's no point in having AAS. If you have questions on that, go ahead and ask me to talk about it again when we are in class. So let me go ahead and show you some examples here. If we were trying to prove that these were similar, you'd be using all the same things in your geometry toolbox, but now you're trying to lead to AA, SAS of similarity, or SSS of similarity. So on this one, we have a given, and then we also know we have the vertical angles theorem. Did that lead to AA or SAS of similarity or SSS of similarity? It did. It led to AA. So yes, those are going to be similar by AA. The next one we look at, we're trying to prove that this triangle is similar to that one. Still use the things from your geometry toolbox. We have a shared angle. So by the reflexive property, we have one of our A's, and I'll redraw the two triangles. That's congruent to that. And then next, by the corresponding angles theorem, those are congruent. So that's a second A. So that one would be yes by AA as well. AA is the easiest out of all of them because you're not having to show proportions. Now let me go ahead and show you what I mean by the proportion aspect of the S's in these. So this one has sides and an angle between them. So it is kind of in the running for SAS of similarity. But what we have to do is we have to look for the proportionality aspect. We know that right angles are congruent, so we have the A part. Now let's look at, is 14 over 28 equal to 5 over 10? Are those proportional? 1/2 and 1/2? Yep. So you have to have that in your explanation before you can get to the point where you're able to use an S in your explanation. So if you have an S, meaning you're using SAS of similarity or SSS of similarity, you need to show the work showing that those sides are proportional. Now, if we look at this, it looks like we're only talking about sides. So maybe it is SSS of similarity. I'm not quite sure though. You have to check it. Does 26 over 13 equal 26 over 13 equal 30 over 15? This one reduces to 2 over 1, that one reduces to 2 over 1, and this one reduces to 2 over 1. Are all the sides proportional? Yep. Therefore, we have Sss of similarity. Now, it's important for you guys to understand congruent figures are also similar. The reason why congruent figures are similar is if you went over, if these were all 26 and 26 and that one was 30, you would just have 26 over 26 equals 26 over 26 equals 30 over 30. And they would be proportional. The scale factor would just be 1. So, like in this case, when you see that these are congruent, that means that they're proportional with a scale factor of 1. We also have the vertical angles. So right now I have an A and I have the proportionality aspect of an S. Is there anything else? There is nothing else, so that one would be no. I want you guys to try this one. I'll tell you right now, the answer is yes, but I want to know, why are these two similar? You should have gone over and seen the vertical angles, and then you should have also seen the alternate interior angles. So we have sides and we have a transversal. So if you were doing a 2-column proof, you would have gone through this process and said the angles are congruent by vertical angles theorem, and then the other angles are congruent by AIA, and then you would have finished by saying the two triangles are similar. Triangle is similar to triangle. Obviously, you would have all the points in there, though. You would have said on this one, finished by AA. All right, so that's how you prove similarity. AA, SAS of similarity, and also SSS of similarity. Go ahead and plug in my computer because it's almost out of battery. And I plugged in. All right, so let's go to the next page. Now here is an example of some actual proofs. So on this one right here, if we wanted to write out the full entire proof, first you come up with a plan and then you start going from there. This is the same proof we just talked about. Vertical angles being congruent, alternate interior angles being congruent in AA. So let's go ahead and just write that into a 2-column proof. If we know MP is parallel to AC, which is given, then that is going to tell us angle A is congruent to angle P. That'd be by AIA theorem. Now technically we could do AIA theorem again for angle C and M, but I'm going to go to vertical angle theorem because I just like it. Angle CBA is congruent to angle PBM by that. And then we would end up with triangle ABC is similar to triangle PBM by AA. You're always hoping to be able to get AA just because it's easy. You don't have to show any proportions, and proportions can get a little tricky when you guys are doing like these actual 2-column proofs. I want to jump down to this problem right here, just that we don't end up with like a 30-minute video. On this one right here, this is going to give an example of how you would use SAS of similarity or SSS of similarity with a proof. So what's going to happen is they're going to tell you one of the sides is equal to a certain percentage or a certain fraction of another side. And then they'll also talk about another set of corresponding sides where one is like a part of the other. So let me show you how this works. Step one is the given. They say that PQ is 3/4 of PR. That's just given. Now, the goal here is we're going to get two different proportions equaling the same fraction so that we can use substitution. So right now I'm getting this 3/4 by itself. So how do you get rid of this PR if PR is being multiplied by 3/4? What would you have to do to both sides to get to this step? Division, prop of equality. Now, when we did proofs back in chapter 2, why did we ever want two things to be equaling the same exact amount, whether it was when we had two things equaling 180 or whatever it was? The reason why we want that is if this one equals 3/4 and this one also equals 3/4, then they must equal one another. So that means that if we look at this, PQ over QR must equal PT over PS. And that would have been substitution. Now, what did I just do? I just showed that two sets of sides were going to be proportional. So I showed that this side over that side equals this side over that side. So I have two S's now. We also know if we're talking about this triangle and this one, that that angle is shared. So angle P is congruent to angle P. That would be which property? Reflexive prop. And then from there, what we would do is we'd be able to finish our proof. Triangle PQT is similar to triangle PRS. And it looks like we have a side proportional to a side, an angle congruent to an angle, a side proportional to a side. This one is going to be 3/4 of that one. This one is going to be 3/4 of that one. So we can finish with Sas of similarity. Once again, write down the given. Go over and get it so that the fractions equal one another. And they're by themselves on one side of the equation. Therefore, you can set them equal to one another and then finish up your proof. All right, I hope that made sense. This one we'll just discuss. As I said, I don't want to take way too long because I do have one other thing we have to talk about for this section. We know if this is a midpoint, it is going to be half of that one. If this is a midpoint, or not midpoint, mid-segment, then it's going to be half of that one. And if this is a mid-segment, it's going to be half of that one. So if I wanted to do this, I could say BC equals 1/2 of JK. AB is equal to 1/2 of KL. And AC equals 1/2 of JL. Using the logic, what do you think the next step is? You can scroll down in your notes, look at your notes. Once we had this, what you would do is divide by JK so that you can get the 1/2 by itself. Divide by KL so you can get the 1/2 by itself. Divide by JL so you can get the 1/2 by itself. You will then have BC over JK equals 1/2. You would have AB over KL equals 1/2. And you would have AC over JL equals 1/2. If they all equal 1/2, then they all equal one other. BC over JK is going to equal AB over KL, which is going to equal AC over JL. So having all these proportions, how do you think you're going to finish your proof? Sss of similarity. Because you have all sides proportional to all sides. All right. One last thing that we have to look at is actually more of an application of the lesson that we did in 7.2, but they left it for here. Now, what we are going to be doing is we are going to be talking about using indirect measurement. Direct measurement is doing exactly that. Let's say you're trying to measure a flagpole. Direct measurement would be climbing to the top, dropping a measuring tape down, and finding out the height. Indirect measurement is using proportions, usually, using proportions / ratios to measure an object. So you probably remember using SOHCAHTOA trig ratios in Algebra 1 and also in Heinz's class. This one has more to do with using like shadows. So if you look at this, it says John is trying to determine the height of a flagpole indirectly. He places a mirror on the ground and walks backward until he sees the top of the flagpole. If he is 5 foot tall and 6 feet away from the mirror, and the mirror is 30 feet from the flagpole, then how tall is the flagpole? So the reason why triangle 1 and triangle 2 would be similar is we already know that these angles are going to be the same because the light bouncing off the mirror will make these angles the same, and both the person and the flagpole are standing at 90 degrees. That means by AA, the two triangles are similar. Now that you've created your two similar triangles, we can set up a proportion. 5 is to x as 6 is to 30. And you could just solve this, getting 6x equals 100, no, not 150. That would give you, yeah, 150. And then you would divide by 6 and divide by 6, and that would give you your answer. 150 divided by 6 is 150 divided by 6 is 25. So the flagpole would be 25 feet tall. This actually works too. So let's say there was like a big tree in your backyard, and somebody was going to come and cut it down and they were charging by the height. You probably wouldn't want to just rely on them to tell you what the exact height is. You go over and set a mirror on the ground and keep stepping backwards until you could see the top of the tree in the mirror. Figure out your eye height, distance from the mirror, mirror distance to the tree trunk, and then you would be able to indirectly measure to the top of the tree. It's really cool. Now, one other way that I want to note as we finish is going to be, let's skip number 2 and look at number 3. You can also use shadows. As long as you do the process pretty quickly, you can use shadows to get similar triangles. Watch this. You have the sun, and the sun is shining down, casting a shadow. A 6-foot man will cast a shadow of 10 feet. Now this tree over here, which we don't know the height, casts a shadow of 60 feet. Since the sun is shining down at the same angle, it creates two similar triangles. Once again, this thing is standing up at 90 degrees, that's standing up at 90 degrees, and this angle right here between the top of the person's head and the sunshine coming down, and the sunshine in the top of the tree, that makes it so the two triangles are congruent, or not congruent, similar by AA. Once we know they're similar, we can use proportions. 6 is to x as 10 is to 60. And then you would solve. You would get 10x equals 360 divided by 10, and you would get 36 feet. We could also use unit analysis like Heinz loves to do, and that could go over and make sure that we're doing the process correctly. But maybe we could do one of those in class. So anyways, as you guys can see, you can use shadows to figure out heights of things indirectly. You can use mirrors. And then the most important part of today's lesson comes down to this, making sure that you understand that just like we could prove triangles were congruent using shortcuts, there's actually shortcuts for similarity as well. There's AA, Sas of Similarity, and SSS of Similarity. Remember that if you do SAS or SSS of Similarity, you have to show proportionality. It's not going to be that the sides are congruent, it's that they're proportional. All right, jot down any questions you have, and I will see you in class to go over this. Adios.